Hello everyone. So today we're going to talk about capacitors, and we're just going to go through the basics of operation and derive the VI characteristics, that is the equation that relates the voltage and current in the capacitor. So by now you all should already have some idea of what a capacitor is. Essentially, it's a device that stores energy in an electric field, and it does this by building up opposing charges on opposing surfaces. And everything you know has some capacitance, even you. So there are capacitances between surfaces, there are capacitances between transmission lines and the ground, there's capacitance between you and the electrical outlet in the wall. But when we talk about capacitors, these are devices which are specifically designed so that the capacitive effect dominates the response of the device. Just like a resistor is a device which is designed so that the resistive effect dominates the response of the device. And capacitance, as you all should know, is measured in farads. So basically, the capacitor operates by having two surfaces which are near to each other, two conducting surfaces near to each other, and they're separated by an electrical insulating medium. So you all should know this equation from secondary school, that is C is equal to epsilon A on D. This relates the capacitance to the area, the surface area of the plate, the distance, and the electrical permittivity. So that is one equation which gives you the capacitance in terms of the geometry, and the capacitance could also be related to electrical quantities such as charge and voltage, and you should know that C is equal to Q on V. So this should all be familiar to you already. So you know that C is equal to QV. If we consider an incremental change in voltage dV here, it should cause some incremental change in charge dQ for some capacitance C. Now, I know Q is equal to CV. I also know that this change in charge over time constitutes a current. So I know Q is equal to IT. In this case, an incremental change in Q over an incremental time. So dQ is equal to I dt. And I could just substitute this in here, and I'll get IT dt is equal to C dV dt. C dV. And notice the mistake I just made, I said C dV dt. This is not dV dt, this is dV of t, which is the voltage is a function of time. Similarly, the current is a function of time. So if I just rearrange the equation, I take the dt and carry it to the other side, I should get IT is equal to C dV dt, or in integral form, Vt is equal to 1 on C, the integral of IT dt. And what this tells me, this one in particular, well, it's the same, both equations are the same, but this one you see it more explicitly. What it tells me is that the voltage across the capacitor cannot change instantaneously. So even if there is a huge current, if I have a step-in current, because I'm integrating between the limits of t0 and t1, if it happens instantaneously, that means t0 and t1 are the same value, then the value of the integral is going to be 0. So the voltage would not change regardless of how big a current is going into it. Instantaneously it cannot change. So let's see what this actually looks like and why this happens. So if I have a capacitor here, and you see I have both plates are neutral and have net neutral charges, so 2 negative and 2 positive on each plate. It is currently disconnected from the source. I'm going to close the source, and then what happens is this voltage across here is going to start attracting it's going to start attracting the charges. So we have a positive voltage here and a negative on this side. So it's going to start attracting the negative charges. And when it does that, as it does that, it builds up the electric field. So let's look at that again. So when I switch the switch on, then slowly the charges begin to come across and the electric field builds, and I get some voltage across the capacitor, and then some more voltage across the capacitor. And this is how the voltage across the capacitor gradually increases until it gets to the supply voltage. What is missing in here is a resistor, and the line has resistance, and that's what is going to isolate the supply voltage from the capacitor voltage. So this is going to happen. The charges are going to keep flowing from one side of the capacitive plate, one side of the capacitor to the other, until the voltage across the capacitor is the same as the supply voltage, and then no more current would flow. So that is basically the operation of the capacitor. By now you should be able to describe that operation in terms of the VI characteristics, and you should also describe what happens in terms of the charges moving from one plate to the other. Next time we're going to look at combining capacitors in series and parallel.